So today's a review class. I'm not teaching, all I'm doing is answering questions, and the longer it takes, the more the period we fill up, the better. So you could be forgiven on this chapter for wondering, do I need to study this? Because so much of what, not all of it, but a lot of the stuff that Gary wrote maybe is something that's a little bit superfluous or ambiguous. So if you have questions about do you need to know that, that's fine. One of the things you should use as a sort of a guidepost, do I need to know it or not, is to have focus on it. So if I told you don't worry about this, then don't worry about it. But I didn't say that about everything in the chapter. But effectively, if I spent time on it, like if I diagrammed, or if I say write this down, or if I do something on the board, particularly if it's not in the book, that is something you should pay attention to. And that therein kind of underscores the benefit of having a notebook. Because obviously if you're writing stuff down, it's me teaching, and if I'm teaching it, it's important, which means it's probably more than likely that something associated with that's going to be on the next test. The reason we're not doing the review class on Wednesday is because wherever possible, I'd like to give you a full review period. If we don't fill the whole day with review questions, I don't know if I'll start chapter 3, but I might make a reference to it, because I will be starting chapter 3 on Wednesday. It's just nothing on 3 is going to be in the chapter 2 test. Format as a test is the same as the last one. It'll be the same as all of them. There's a multiple choice section, then there's a written response. Okay? So, ask away. What can I help you with? Yeah.
So for homogeneous mixtures, what's the difference between solution and colloids, and for heterogeneous mixtures, what's the difference?
All of the differences down that heterogeneous pathway for mixtures are size of component particles. So the particles in the solution are smaller than the colloid. And the best summary of that, without worrying about the actual numbers, is the table that Gary gives you on page page 76. So he says that there is no hard and fast distinction between where a solution ends and a colloid starts, or where a colloid ends and a suspension starts. See it as kind of a spectrum. The component particles get bigger. If they're small enough that they don't reflect visible light, then they're a solution. And you don't have to remember that the particles aren't bigger than a nanometer. It's just they're not small enough to reflect visible light solution. As they get bigger, they don't settle out upon standing, but they are big enough to reflect visible light. That's a colloid. The other difference between a colloid and a solution is you can centrifuge a colloid and the components will separate. Not so in a solution. And in terms of a colloid going to a suspension, then we go from homogeneous to heterogeneous, okay? And as that table suggests, yeah, there's still the Tyndall effect, but also they settle out upon standing. And that means it's a suspension. A colloid won't do that. The particles aren't big enough to settle out. They are big enough to separate by a centrifuge, and they are big enough to reflect light, but they're not big enough to settle out upon standing. So see it as kind of a sort of a progression. I'm not going to expect you to remember sizes, micrometer versus nanometer. Just see it as kind of a progression. And wherever possible, I like to avoid memory. There's enough memory in chemistry that with that type of thing, is it a distinction? Yes. It's just that I wouldn't lose sleep over, differentiating between where a colloid starts and where a solution ends, that type of thing. Okay? Yeah.
Can you explain what the Tyndall effect is?
The Tyndall effect? Tyndall effect is when you shine a light through a liquid. You see the beam of light. Now, why is that? Well, if the particles in that mixture are bigger than the wavelength of light. Now, you don't need to know that, but visible light has wavelength about 10 to the minus 7 meters. If the particles in that liquid are at least that big or bigger, then when the light hits them, they'll reflect it. And that's the Tyndall effect. You see the beam of light going through it. If you shine a flashlight through a solution of salt water, you don't see anything because the particles, the components, are far smaller than the wavelength of the light, which means they don't affect the light at all, and that's why you don't see the beam. You're only going to see a beam if there's something in there reflecting it, and they don't reflect unless they're big enough. So a suspension and a colloid, they'll both have that. You'll see the beam of light going through it, but not in a solution, okay? But again, that's all just based on size of particles. Yeah.
Can you explain on page 63, it says, a solid can be immersed indefinitely in its own liquid because its rate of melting equals its rate of freezing?
Say that again?
Can you explain on page 63, like it says, a solid can be like immersed indefinitely in its own liquid because its like rate of melting equals the rate of freezing?
If you have, say, an ice water bath, as long as there's ice there, as long as there's a significant amount of the ice in the liquid, the rate of freezing is the same as the rate of melting. So in other words, if the ice is melting, the temperature isn't changing because all that's happening is potential energy is going down. As the water is freezing, the temperature isn't going down because the potential energy is all that's changing. So effectively what he's saying there is a liquid at 0 degrees when an ice water bath, you're on that horizontal line. The rate of freezing matches the rate of melting. And as long as that's happening, the only change will be potential energy, which means there's no temperature change. Which actually kind of brings us under the heading of what did I focus on and what might you want to pay attention to. This thing. So if you look at the heating curve, this is on the bottom of page, let's see, 64. This is an example of where I added to something that's in the book, which suggests or should suggest to you that it might be important. Regardless of these temperature landmarks, any substance whose temperature remains constant during a phase change, whether it's melting or boiling or freezing, is pure something. And if the temperature remains constant, it means the only thing that's changing is potential energy, not kinetic. Remember, kinetic energy is a measure of, or temperature is a measure of average kinetic energy. If the temperature is not changing, neither is the average kinetic energy. So in this diagram, Gary's simply adding heat. So you're adding energy. Here, the energy is going in decreasing kinetic. Why? Because the temperature is going up. So the particles are moving faster and faster. At the point where they're moving fast enough that now in the solid phase, they overcome the attractive force locking them into place and now can move around. Now all the energy that's going into it is potential. And you know that because even though you're adding heat, temperature's not going up. So the heat of, in this case, the heat of fusion is the increase in potential energy when the phase changes. The fact that it's a horizontal line means there's only one thing in there undergoing that change. Nothing's speeding up. All that's happening is attractive forces are being overcome. That's why this is potential increase, kinetic. Here, still kinetic, because the temperature's going up. As soon as the boiling starts, we're still adding heat, but all the heat that's going into that liquid is overcoming the attractive forces of the liquid molecules, turning into a gas. And as long as there's liquid for that to happen, all of that energy is simply going into potential. The temperature only goes up when there's no more liquid. And now what we're doing is increasing the kinetic energy of the gas molecules. All right? Now Gary didn't add that there, but he did add this. Notice the heat of fusion compared to the heat of vaporization. Heat of vaporization is always more, because potential energy is all that's increasing here, but the amount of potential energy increase associated with taking liquids and completely overcoming the attractive force and turning them to gas is way bigger than simply taking a crystal and melting it. The particles are still in contact with each other after this. So you've increased the potential energy because they're not locked in place, but you haven't physically separated. That's why the heat of vaporization is always more than the heat of fusion. We added something to this as well. We talked about, okay, what if you have an impure substance, like a sample of ice contaminated with sodium chloride? Well, you're still going to get the heating current, except when the phase changes, you're going to get a temperature change. What does that tell you? It means there's more than one thing in there. There's something that's undergoing a potential energy change. How do you know? Because the phase is changing. But there's also something in there increasing in kinetic. How do you know that? Because the temperature's going up. So this has to mean a mixture. And notice the other change is not only is there a temperature change during a phase change, but that happens at a different temperature. Even when you're finished melting, you're still below what the melting point would have been with pure ice. Then we talked about boiling point elevation. It starts boiling at a higher temperature, and the temperature will go up as it's boiling. Once again, symbolizing that there's more than one thing in there. If you get a temperature change during a phase change, it's impure. If you don't, it's pure. Regardless of where those temperatures happen, it's pure if there's a horizontal line during a phase change. If we talked about heat being removed, it's the mirror image of this thing. So let's say we started with pure water, hot water, close to boiling point, but not boiling, and we cooled it. It's going to start freezing at zero. What's happening as we're removing heat? Kinetic energy is going down. That's why the temperature is going down. We're removing heat here, but we're not lowering kinetic, we're lowering potential because attractive forces are forming. And then, once it's all frozen, now the temperature drops again. Now it's decreasing kinetic. So, heat added or removed. If it's removed, then we got a cooling curve. And if we have salt water, it's going to mirror this thing. It's going to start melting below zero, and then its temperature is going to go down while it's melting. It'll look exactly like this in a mirror. But again, the temperature change during a phase change means it's impure, because you've got something undergoing a phase change, but you also have something where kinetic energy is changing. All right? So that's an example of, yeah, maybe you wanted to write that down. Maybe you wanted to jot some stuff down, because it's likely something like that might appear in some form on the test. Yeah.
So for the impure substance, when it's the cooling curve, when it starts melting, it's below zero.
It's freezing. If you're cooling it, it's not melting, it's freezing.
When it starts freezing,
Yeah,
it's
below zero.
below zero, but above the point where it starts to melt. Because like when it's graphed
Okay,
here,
let me clarify. Melting and freezing are the same thing, just approached from different directions. Okay? So for the impure substance, let's say it's salt water. It's going to start freezing, not melting, freezing below zero. And then as it freezes, the temperature is going down. That means there is something slowing down in there, which isn't the water, but there's also something changing phase, which is the water. All right? And that is the mirror image of what we would see if we heated the ice contaminated with sodium chloride. We'd start melting here and continue melting until all the solid's gone, which will be the same temperatures here. So literally, it's the mirror image, okay? But everything you can say about removing heat is adding heat in the opposite direction, okay? Yeah.
Do we have to include like condensation? Like the opposite of?
Probably not. I mean, it would mirror this, but you would have to start with steam and cooling it. So probably not. Because by the time all the gases, all the liquid's gone, you have solid table salt, right? In other words, this vapor is pure water vapor. The salt's left in the bottom of the container. So it's kind of hard to have the salt and the gas. It wouldn't be there, all right? Yeah.
Could you re-explain recrystallization, I think?
Could I what?
Re-explain recrystallization.
Recrystallization is really a purification technique used when you've got two solids mixed together, where the vast majority of those solids is one. So it's like 99% one, 1% the other. So you add enough water to dissolve them, okay? Just enough water to form a solution. In that solution, the vast majority of the ions are of one type, and a tiny amount of the ions are of the other type. So in other words, the solution's almost saturated with the ionic compound that you had the most of. And as you cool it, as you slowly heat it, once it's liquid, now what you do is you start evaporating it. And as you evaporate it and the solvent leaves, the first crystals that you form have to be the one that you had in the greatest amount, like 99%. And so that separation technique isn't based on solubility, it's not based on boiling point, it's not based on density, it's based only on concentration. And you can't evaporate it to dryness, because if you do, you're gonna be right back where you started from. Now that was one of the two things I mentioned that Gary didn't discuss. He might have mentioned recrystallization, but he didn't describe it. He also might have mentioned extraction. He didn't call it solvent extraction, but I explain that as well, okay? Solvent extraction is based on solubility. Recrystallization is based on concentration. So try to connect what the separation technique is to what property or properties it's based on. And remember, the separation technique we ended with was chromatography, which is based on two things. Not only solubility, but also how well the mixture components adhere to the stationary phase, the paper, in this case. And by the way, I'm in the process of marking your labs. For the most part, what I've seen is pretty good. The lab, pretty good. The issues are really just people reading the questions carefully, okay? But the fact that there were calculations in the lab report means there could very well be calculations on the test, all right? And remember, for example, an RF equation, as many variables as there are in an equation are the ways that the equation can be written. So if I give you this and this, obviously you should be able to calculate RF. But if you give you these two, you should be able to calculate that. If I give you those two, you should be able to calculate that, right? And we talked about the separation distance thing already. And most of you, again, what I've seen in the lab, everybody's doing fine on separation distance. But remember, that could be something that you see one way or another on the test. It could be a multiple choice, it could be written response, it could be both. What else?
Where on the cooling curve do we know where to mark the temperature is starting to freeze?
Cooling curve?
Yeah, for impure and pure substances.
Right there, freezing starts.
Freezing starts at 100 for pure?
No, freezing starts at 0.
Okay.
And as we're going from here to here, the amount of liquid's going down, the amount of solid's going up. So by the time it's here, there's no more liquid. If we're heating it, melting starts here, and as we're going this way, the amount of solid goes down, the amount of liquid goes up. So when we see the last solid disappear, now it's all liquid, now the temperature starts going up, because now it's just kinetic increase, right? But if you don't see a temperature change during a phase change, regardless of what these things are, it's pure something, all right? That's one of the ways we assess purity, if you don't see a temperature change during a phase change. Yep.
Will we have to know what an allotrope is?
No, don't worry about an allotrope. Allotropes are just different form of the same element, like graphite and diamond are both pure carbon. They're both elemental carbon, they're just different forms. Yeah.
How in-depth on boiling point do we have to? It's like, there's a lot on it in the textbook.
I think the best definition of a boiling point is the point at which the vapor pressure of the liquid equals atmospheric pressure. Now, you don't have to draw a vapor pressure curve, but does that definition make sense? Yeah, think of the boiling pot of water. The bubbles stay inflated all the way to the surface, which means that they have enough pressure inside them that the atmosphere isn't able to collapse the bubbles. So if the pressure inside the bubble matches the atmospheric pressure, they stay inflated all the way to the top. That's boiling. Unless they make it to the top, the liquid's not boiling. Will you have to draw vapor pressure curves? No, you won't. Okay? The only thing I disagree with in that is Gary tells us that at the boiling point, the kinetic energy of all the particles are the same. That's impossible. It can't ever be all the same. The fact that you've got a liquid and still colliding particles, kinetic energy cannot be the same. It may be the highest temperature, but that's the highest average temperature. There are still variations in it. Yep.
Can you repeat the definition of boiling point?
Temperature at which the vapor pressure of the liquid equals the atmospheric pressure. And if you want a nutshell version of that, the bubbles stay inflated all the way to the top of the liquid.
Do we need to know the melting and boiling points of different elements?
The melting and boiling points, like on page 65?
Yeah.
God, no. What is the big takeaway from the table on page 65? Well, two things. One of the things it shows you is that the heat of vaporization is always more than the heat of fusion. In other words, this is a much bigger increase in potential energy than this is. Why? Because when you vaporize a liquid, you completely separate the particles. That's a huge increase in potential. So that's the first takeaway. So heat of fusion is always less than heat of vaporization. Second takeaway is fusion and vaporization are physical changes. The amount of the energy change associated with physical are never even close to chemical. So that's the other takeaway. If you look at the two columns on the right, heat of combustion, heat of formation, those are chemical properties. And the amount of energies associated with those are massive compared to physical. But do I care if you remember the numbers? No, don't remember the numbers. There's tables with that stuff in it, in data booklets. It's just the takeaway here is vaporization always involves a greater increase in energy than fusion, and chemical changes always involve way more energy than physical. That's all.
Do you think you could go through question 6 on page 67?
Question 6. I wouldn't worry about that. I disagree with some of Gary's interpretations here. He's not wrong that whether you classify it as intensive or extensive is sometimes based on how the information is provided. But to go into the minutia associated with when and when not is more than you need to concern yourself with. I would simply say, if it's an intensive property, it doesn't depend on the amount of material, and it can be used to identify it, like density, boiling point, melting point, specific heat. If it's an extensive property, it can't be used to identify the material, and it does depend on the amount of material, like mass or volume, that type of thing. That's all right? There's definitions that need to be understood, incorporated into stuff we're learning, but some of them are just definitions, and the Mark and Ken shouldn't rise or fall on your ability to memorize that kind of minutia. Yeah.
So are any of like the questions, like just continue coming from the study
Any review questions that relate to what I focused on? Yeah. If I didn't, or if I told you specifically, don't worry about these, then don't worry about it. That's the best way to answer the question, do you need to study it? Did I focus on it? Or did I even elaborate on it? Or did I add to it? Then the answer pretty much is yes. Yeah.
Is developing a program just like making it?
Say that again?
If you develop a like
Chromatograph?
Yeah.
Yeah.
What does it mean to like develop it?
Watch the color separate on the paper. So you guys did that. Every one of those things when you took it out was a developed chromatograph. Yeah.
There was a point where we went to chapter 6 and page 311 and 12.
The properties of metals and nonmetals?
Yeah, the strength of ionic versus covalent bonds.
I wouldn't worry too much about that yet. That was basically to confirm that just because it's a covalent compound doesn't mean it exists as molecules, okay? Most covalent compounds are molecular, but the terms are not synonymous. And the example we used was silicon dioxide, which is quartz. And the formula is a ratio, which is unusual for covalent compounds, but that's because no molecules exist in quartz. It's a network covalent cell. And that's why I said when you see molecular, cross it out and write covalent. Because covalent doesn't always mean molecular. Also, you don't need to worry about difference in electronegativity. The only reason I mention that is to confirm that just because it's metal and non-metal doesn't mean it's ionic. If it's a metal from the left and a non-metal from the right, yeah, ionic. And if a bond is ionic in a binary compound, it has to be metal and non-metal. It's just because it's metal and non-metal doesn't always mean it's ionic. And Gary, when he introduces stuff, sometimes I think he goes a little overboard with his absolute always, never. Because chemistry is full of exceptions. And it seems to me, in this chapter, I spent a lot of time debunking some of those generalizations. They may often be true, but often it's not the same as always. Okay? And a lot of the stuff I've had to do to sort of correct it, we will elaborate on in subsequent chapters. Okay? Yeah.
I remember you were talking about phase equilibrium or
Phase equilibrium?
yeah.
That's only in the context of vapor pressure. In other words, when in a closed system where we have a liquid and it's gas, when the rate of evaporation equals the rate of condensation, that's a phase equilibrium. But don't worry about that. That was how we built up the definition of vapor pressure.
Oh.
Yeah, so don't worry about equilibrium at all. That's great. Yeah. Yeah. As far as you're concerned, if they are within 3 of the nearest noble gas, 3 what? Well, 3 electrons. So for example, argon's got 18. Phosphorus is 3 short. So the charge on a phosphide anion is 3 minus. Sulfur is 2 short. So a charge on a sulfide anion is 2 minus. It needs to gate 2. Chlorine is 1 short. So the charge on the chloride anion is 1 minus. If you have a cation, it means it's giving electrons away. So for example, aluminum in its position in the table might look like it's easier to gain electrons, but if you look at the number, that's 13. If it loses 3, 1, 2, 3, it looks just like neon. So the charge on an aluminum ion is always 3 plus. As long as you're within 3 of the nearest noble gas, you can usually predict the charge of an ion. And we use an example here, strontium. Strontium isn't on your table, but it's in the same group as calcium and magnesium, each which lose 2 electrons to be like the nearest noble gas. That's all strontium ever does as well, 2 plus ion. Same with barium, 2 plus ion. Same with beryllium, 2 plus ion. Because by giving away 2, on the outside, we look like a noble gas. Yttrium, that's not on your table. Yttrium's got 39 electrons. If it gives away 3, it's got 36. So what's the charge on an yttrium ion? 3+. Yeah, it's that simple. Now, does that mean there's no such thing as 4 plus or minus ions? No. It's just that they're not that common, because it's not easy for something to give away 4 electrons. Every time you give away 1 electron, what you're left with is positive. And the more electrons you take away, the more positive you're left with. It gets harder to take electrons away. As far as the transition metals are concerned, you don't have to predict any of their charges, because they're on the table of ions within a group. But if you see a transition metal ion with more than 1 charge, you know you need a Roman numeral when you write the name. If you see a transition metal compound name with a Roman numeral in it, you know the charge. So for example, cobalt isn't on your table of polyatomic ions or transition metal ions. But let's say I gave you the formula, or let's say I said write the formula for cobalt 2 chloride hexahydride. As soon as you see the 2, you know cobalt, number 1's multivalent, but you also know what the charge is, 2+. But the only transition metal ions whose charges you need to know are those on the table. Okay? And you can't tell just by looking at the table why zinc is always going to be 2+, or why silver is always going to be 1+. And once we learn quantum mechanics, you will be able. It's just that you can't do that now. Okay? What else? Yep.
Did you go over the definition of vapor pressure?
Vapor pressure. The pressure of a gas exerted when it is in equilibrium with its liquid. But I just said you don't need to know that. Okay? Don't need to know. And nor do you need to worry about the vapor pressure curves. Okay? I only mention that because Gary mentioned vapor pressure in his definition of boiling. So I thought I'd draw the curves on the board for you, but I will not ask you to draw vapor pressure curves. Okay?
On page 75, for polars, it mentions a dispersed phase. Like, what is a dispersed phase?
Dispersed phase is like, this is page 75?
Yes.
Okay, so if you compare solutions to colloids, in solutions, we have a solute dissolved in a solvent to make a solution. In a colloid, we don't use those terms. We use, instead of solute, we use dispersed phase. Instead of solvent, we use continuous medium. And instead of solution, we use colloid. So a dispersed phase is dispersed in a medium to make a colloid, like a solute is dissolved in a solvent to make a solution. So we don't use the word dissolved in. We use dispersed phase, dispersed in a medium. That combination equals a colloid. Solute dissolved in a solvent equals a solution. Yeah. Again, but that's terminology that I probably wouldn't expect you to articulate. Okay? He's not wrong, it's just if we focused on everything he gave us here in this section, not just the chapter, this section, there'd be way too much memory involved, and I don't want that to be what chemistry's focused on. There'll be memory coming up, but don't worry about this stuff.
Also on page 84, it talks about developing another ground by spraying chemicals.
Don't worry about that. Just the only chromatography I want you to worry about is the paper one we did. There's lots of different types of chromatography. Yeah. I would, as your guide for chromatography, I would use your lab handout. Gary's measurements diagrams are also wrong too. You don't go from the center of the spot, you go from the edge of the spot. Yep.
What is an anhydrous salt?
What is a who?
Anhydrous salt.
Anhydrous.
Anhydrous.
Anhydrous means without water. So for example, if we have copper 2 sulfate pentahydrate, that's that blue solid. If we heat it and drive all the 5 water molecules off, then it's anhydrous without water. And then it's wet. So anhydrous are salts without water molecules in them. They're non-hydrates, if you will. Yeah.
How do I know a compound is organic or inorganic?
Don't worry about organic and inorganic just yet, okay? We'll talk about organic chemistry in spades when we get to chapter 8. You should know the difference between binary and a non-binary, and a base and an acid and a salt, but I wouldn't worry about organic or inorganic just yet. This is a more productive review class than we had last time, yeah.
On page 60, it talks about there's a difference between thermal energy and temperature. Can you let that explain it?
Temperature is average kinetic energy. It doesn't depend on the amount of material. Thermal energy depends on the total amount of energy. So that Gary uses the example of a bathtub full of cool water has more thermal energy than a cup of boiling water, because the amount of energy is obviously depends on the amount. Temperature, though, doesn't depend on the amount, okay? But Gary also uses that to say, therefore, temperature is an intensive property. He and I differ on that one, because I think an intensive property should satisfy two criteria. It doesn't depend on the amount of material, but also it can be used to identify the material. And just because something's got a temperature of 50 degrees doesn't mean you know what it is. All it means is it doesn't depend on the amount of material, but you still can identify it. Yep.
Will we need to know like different types of desiccants?
No. A desiccant is an anhydrous salt that will grab water if it can find it, all right, like usually out of the atmosphere. And there's a term there called hygroscopic, which is the process of that doing it, but don't worry about that, okay? No. Just, from that, just know how to name hydrates, or if you see the name, write the formula. Which reminds me, if, as I've said several times, if you were one of those people that struggled on formula writing and naming in grade 10, try to do as many of the sample problems and, or the practice problems and review questions as you can and check your answer. That's, it wasn't gone into in the same level of detail as it was in grade 10, because we've assumed you've been given it, and that also back in grade 9. But again, the fact that I didn't teach most of you, I don't know if you had trouble with that stuff. But there will be questions on this test on formula writing and naming. Yeah.
On page 96, after about the subjects presented, there's a paragraph that says it's worth mentioning that the term acid is sometimes ambiguous in that it may refer either to the compound or its solution. What is it referring to there?
Where are you reading from?
Page 90.
The top of the page?
Yeah. The third.
So again, read that out loud again?
It says it bears mentioning that the term acid is sometimes ambiguous in that it may refer either to the compound or to its solution.
He's not wrong, it's just that none of the acids you will encounter will be anything other than aqueous solutions, okay? So technically, if it's an acid, it should have AQ after it. And a great example of that is this. Some people will often call that hydrochloric acid. That's a gas. It's not a liquid at all. But as soon as you put it in water, it becomes an acid. So I would prefer that you assume that all acids are aqueous solutions. Yeah.
Are we gonna need to know anything about froth location?
No, you don't have to worry about froth flotation, you don't have to worry about fractional distillation. Only the ones I talked about, okay?
When we're doing different formulas and compounds, are we gonna need to put the different like A, Q, L, and in brackets afterwards?
The states?
The properties. Like you said that one said acid.
If I ask you for the formula for hydrochloric acid, if you write this, you're probably okay. But if I give you that, don't call it hydrogen chloride. It's hydrochloric acid, okay? And how do you recognize the formula for an acid? It starts with H, or it ends with COOH, okay? So either that's how the formula ends, or that's how the formula starts. The only exception here is water, okay? Obviously, water, H2O, that's not an acid or base. That's an organic acid, and there's far more of these than there are of these. But again, we'll get into organic acids and organic acid naming later on.
Doesn't matter how we write sulfur.
With the pH or F? No. Okay.
Do you have to know how the distillation apparatus works?
Well, you have to know that distillation is based on different boiling points, so basically we boil off one component and then condense it in a condenser. So, will I ask you to draw it? No, but you should, if you, let's say you saw a diagram, you should be able to say where the gas is condensing and where the other material is remaining. So the diagram that Gary gave you on that page, we got the boiling flask, that's where one component's staying, and then we got the condenser and the water or the liquid dripping off the other, that's where the other component is. Yeah.
Can you go over question 14 for teaching science?
Question 14 where?
For the 2.4 review.
Okay. 14. 2.4. I think probably the best answer there is, if we bracket something in an ionic compound, it's a ratio of the ions in the solid, okay? We don't bracket water because they're molecules trapped in the crystal. That's the best way to say it, okay? It represents the actual number of water molecules per formula unit. Bracketing something in an ionic formula tells us it's a polyatomic ion in that ratio, and water's not an ion at all. That reminds me though, remember that the prefixes attached to naming covalent compounds are the same prefixes you need to apply for hydrates. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Those have to be applied to hydrates as well as covalent compounds, right? In grade 10, I think we gave them to you, but there's a new term surfacing now in grade 10. Do we get memory aids? Memory aids to me is like an oxymoron. If it's an aid, you're not memorizing. So a memory aid, that might be, how do I remember this? Think of a little algorithm in your head. But a memory aid, which is effectively a cheat sheet, you're not memorizing at all. So the answer to all those questions is no, you don't get me. Years gone by, you didn't get a table of polyatomic ions. You had to memorize them years ago. So your life is a lot easier than it used to be. And when you get to grade 12, it'll be even more so because years gone by, these ended in 2010. But prior to 2010, to graduate, you needed to write provincial exams. And in their early years, provincial exams were worth 40% of your final grade, and you had to write them. Yeah, there's no more provincial exams, but it wasn't that long ago when there was. And it got even better. Early on in the provincial exams, you wrote a 2-hour provincial exam, not 2.5, 2, and if you didn't finish, tough. Then you got a half hour off, and if you wanted to apply for a scholarship, you had to write a scholarship exam, which was another hour, and it was only written response. And then your mark on the scholarship exam and your mark on the regular provincial exam, those were the things that were submitted, say, to SFU or UBC. So your life is a lot easier than it used to be for students years ago. It may not seem easy, but comparatively speaking, it is. So, yeah.
Do you think you could go through question 13 of the 2.3?
Question 13. Why is a hydrate not a mixture of salt and water? A mixture means that you can vary the amounts. So salt water is a mixture, because you can put a little salt in a lot of water, or a little water and a lot of salt. But it's not a mixture, it's a pure substance, because the amount of water is fixed. So when you say copper 2 sulfate pentahydrate, it's not hexahydrate, it's not tetrahydrate, it's pentahydrate. It's a pure compound. The difference between a pure compound and a mixture is the components can vary. They don't vary in hydrates. Every time you see blue copper 2 sulfate pentahydrate, it's a pure substance. All right? That's the distinction. There's water in there, but it's not a mixture. It's a pure substance.
Do you know polar covalent?
At this point, no. No, polar covalent is just unequal sharing of electrons. And to understand that, you'd have to deal with electronegativity and delta En. That's coming up, you just don't need to know it yet. The only reason I went through that is Gary said that if it's a metal and a non-metal, it's always ionic. That isn't true. If it's ionic, it has to be in a binary compound, metal, non-metal. But just because it's metal, non-metal doesn't always mean ionic, okay? I know he knows that, it's just in his attempt to be simple at the beginning. I think what he's probably doing is asking you to remember what you did in grade 10, when you were young and stupid and your brains were small. We're expanding that now, okay? Yeah.
When you're putting like the prefixes of di or tri in front of iodide, or iodide, would it be with
Hyphen.
two I's or?
No, that when the vowels are the same, only for I, you use a hyphen, like diiodide. For oxygen, you only write one O, like, it's not carbon monoxide, it's carbon monoxide. And don't use hyphens either unless it's di-I. Like, there's no hyphen for tetraoxide or dioxide or that type of thing. Okay? That's a little thing, but it's still a thing, okay? More people have asked questions than the last review class, but there's still a whole bunch of people that haven't. Now, that may mean those people don't have any questions, but I tend to doubt that. Mhm.
Do you know anything about chemical species?
A chemical species is just chemical. That's all that means, a chemical. Water's a chemical species. Nitrogen's a chemical species. Anything that isn't energy is matter, and any matter is a chemical species. So yeah, Gary's just throwing definitions at you. Chemical species, just a chemical. Pick any compound, that's a chemical species. Yep.
Do we have to know anything from the lab?
Yes, absolutely you have to know stuff from the lab. I thought that was obvious. Yeah, you need to know RF values. You need to know what chromatography involves. So yeah. Mhm.
Could you go look at the formation of ionic crystal lattices?
Yeah, when let's say I lower solid sodium into a jar of green chlorine gas, we get some serious fireworks. All the chlorines grab electrons from the sodium atoms lose electrons to the chlorine. Now you have a sodium ion and a chloride ion that can't come apart. And when all of those electron transfers happen, you get this growing three-dimensional arrangement of positive to negative ions that we refer to as a crystal lattice. Okay? And there's no neutral molecules in there, that's why the formula is just a ratio. And you can't really tell by looking at it. Partly you can. Around every positive ion, there are 6 negative ions. One to the left, right, top, bottom, in front, behind. Same with around every negative ion. There's 6 positive ions. Up, down, right, left, in front, behind. And when those attractions extend out in all 3 dimensions, it packs like this, and that's a crystal lattice. And that's why the melting point's so high, because we gotta overcome ionic bonds to liquefy this, right? Every crystal lattice will form that way. The actual shapes they adopt will be a result of the ratio of the sizes and also the numbers. So for sodium chloride, it's 1 to 1. Magnesium chloride, it'll be 1 to 2. Aluminum chloride, it'll be 1 to 3. Iron 3 oxide, it'll be 2 to 3. So that ratio and the difference in sizes means the crystal packing will be different, but it'll still be there. And crystallographers give name to these packing arrangements depending on that. You don't have to know that, but they all kind of look like this, all right? That's a crystal lattice. Yep.
When you say we need to know things from the chromatography lab, do you mean like the calculations, or do we need to know the RF values of different dyes?
You don't have to memorize RF values, but you have to know how to calculate it. And remember, there's 3 ways to write every equation where there's that 3 variables. Given those 2, calculate that. Given that, calculate this. Given those, calculate this. And I also derived an equation for you for separation distance, right? That's not the only way to do it, but I think the vast majority of you used it on your lab report, which is good. Okay?
So you're gonna have to bring like rulers to measure, like where you have diagrams, because there's a question on that.
You know, not like the where you had to put your ruler on the diagram. Interestingly enough, I just marked the lab report. The name will remain anonymous. Where they used their ruler and they said, well, obviously the 2 colors in that chromatogram are blue and red. Except the color is orange. So blue and red doesn't make orange. Yellow and red makes orange. Well, blue and red makes purple. So that's kind of one of those, give your head a shake before you put that in a lab report. And it also tells me that 2 people did that and both think that blue and red make orange, which is like, really? Yeah, so I think I might have written be careful. It's not what I wanted to write, but that's the diplomatic, be careful. Or I might have just, blue and red make orange, question mark? Yeah. There's a few mistakes like that. They're not serious mistakes, but they're one of those, you kind of scratch your head. Really? Yep.
In question 12 of 2.2 review, what does it mean neutral?
Number 12 in the 2.3 review.
2.2.
2.2, you said? Identify each of the following as a neutral atom, ion, or molecule. That one?
Yeah.
Okay. If it's got a charge, it's an ion.
No, yeah, but what is a neutral atom? It's
Just an atom.
just an atom.
Neutral atom. Like oxygen. Oxygen's a neutral atom. N2 is a molecule. They happen to be the same atom, but N2 is what we call a diatomic molecule. Oxygen's just an oxygen atom. D is just an atom. E is a molecule. C is an ion. F is an ion. And all compounds, by the way, have to be neutral. Again, that may be obvious, but you can't go to the chemical storeroom and get a compound that has a charge. You can get compounds that have ions in them, but the compounds always have to be neutral. What else? The test isn't until Friday, so there may be other questions that surface between now and then. Wednesday is not a review class though. Wednesday we're going to start chapter 3. And with some minor exceptions, chapter 3 is really where grade 11 chemistry starts. Yeah, some of the stuff we've been doing in 1 and 2 they're definitely chemistry. We haven't seen them before, but they're not as foundational as what we're moving into in chapter 3. You might remember in chapter 1, Sherry told us that the SI unit for amount of a substance is the mole. Chapter 3 introduces that, and it's not hyperbole to say, as chapter 3 mentions in the title, the central unit of chemistry. Anytime we do quantitative chemistry, calculate with chemical amounts, we involve the mole, okay? Up till now, whenever we've made reference to the periodic table, the number we usually focus on is this, the atomic number of protons, number of electrons in the neutral atom. What we haven't paid much attention to is the mass number. So if you look at oxygen, 15.9994. 15.994 what? Can't be grams, because atoms are far too small to see. And if they're far too small to see, they're far too small to measure. So how is it we know that oxygen is that mass? And what unit are we going to employ? And if they're too small to see and too small to measure, how do we know that nitrogen is less massive than oxygen, or fluorine is more massive than oxygen? How do we know that? We can't see them. We can't measure them individually, so where does that stuff come from? That's a good question. And that's why, to his credit, Gary begins this chapter with relative atomic mass. So, obviously this isn't going to be on a test, but what I'd like you to do for Wednesday, section 3.1 is very short. It's from page 102 to 105. It's like 4 pages. So I want you to read those 4 pages, okay? You might have to read them a couple times. You can ignore some of the language that Gary uses because people don't use words like nifty anymore. But the idea behind the logic attached to relative mass is worth focusing on. And if by reading it, it makes a reasonable amount of sense, then try the practice problems on the bottom of page 103 and the practice problems on the bottom of page 104. I expect that you're going to have a little trouble with that, but that's what we're doing Wednesday, okay? I'd like to think we get through it all in that shortened block. I think we can. But if that logic makes sense, then everything we say after that, and our discussion of atomic mass, molar mass, molecular mass, empirical formulas, all of that will make a lot more sense, okay? We have advisory Wednesday, right? When I heard the topic for advisory, and I've heard it before, it just strikes me as kind of an oxymoron. Academic advisory. You guys know what an oxymoron is? That might apply. So apparently on Wednesday, there are people that are helping and there are people that are being helped, correct? What happens if you're not in either of those categories? What do? Study, okay. I would imagine there is a room where chemistry is being discussed. I don't know who's volunteered to be a chemistry helper. I haven't talked to them. Maybe, given the fact that there's a chemistry test coming up, that might be a good place to spend some time if you think you need help. I'll be circulating, probably. I'm certainly not going to be standing in the gym watching my advisory students sit on the floor. I don't know that you can help anybody or be helped by sitting on a cold wooden floor. But that might not be a bad, for the first time ever, a bad way to spend your time in advisory. Because you might benefit from help. So I suspect there's probably some grade 12 students maybe, or some grade 11 students that are doing well, and have volunteered some time to help. That's awesome. And if I'm in that room, you can ask me. So this might be the one and only time ever where your time spent in advisory would be worth it. Okay. And if something surfaces between now and Friday, whether it's on Wednesday or not, just ask me. It's just we're not spending time on Wednesday doing review again, all right? So if you're fine with the stuff for the test coming up, maybe start on page 102. If you look on page 101 just briefly, by the end of this chapter, you should know the meaning of these key terms. Empirical formula, molarity, molar mass, molar solution, molar volume, mole. Molecular formula, molecular mass, percent composition, relative atomic mass, standard solution, stoichiometry, STP. Most of those are brand new. So if I had to pick, and it's hard, but if I had to pick one word in Chem 11, that's probably the most important, it would be MOLE. So this is one of those times where if you can help it, do not miss class in this chapter. There's too much foundational stuff here. Okay? You're gonna be getting another worksheet in this chapter. It'll be a different worksheet than you're used to, but I will be helping you get through it because it's, again, gonna be foundational. So this will be a different chapter. This will be something brand new. And if this chapter makes sense, then a good chunk of the rest of the course hopefully will make sense. That's how important it is. How many people play senior basketball? You guys are going to Hawaii?
Yeah.
You know how many classes you're missing?
I think we're leaving on the 14th and we was one.
More than one class, so I expect, right?
I think so.
You may want, I only know this because one of the students from the other block asked, you may want to ask somebody to record the lecture. You also want to make very clear you stay in touch with Google Classroom. You don't have to take your book because you got your Chromebook, but hopefully we'll get to a point where enough of this will have been done that what you miss won't be too foundational. It'll just be exercises, but we'll have to wait and see. Okay? I don't think you're gonna miss a test, but 2 full classes of chem are gonna be significant when it's in this chapter. And this is kind of a long chapter as well. So this is the last chapter that Gary wrote, but you know what? He did a pretty good job. He did a pretty good job of this. Chapter 4 is the second chapter that Sherry wrote. And that chapter 4 is done particularly well, except we're not doing all of it. But we're getting a little ahead of ourselves. So feel free to start reading on page 102.